Great. So let's move on to one of two examples here and drive home what we need to do in StatKey. And again, doing some interpretation and thinking about what hypothesis testing is and what these steps are. So let's set the scene for our first example, this thing called matching dogs. So let's say we have this study, and this is in the book, and there are 25 dog owners. And in this setup, there are 25 dog owners and 2 dogs associated with each owner in a picture. And individuals needed to be paired with their correct dog. So it was 1 owner, 2 dogs, and a study subject would need to pick the right dog between the 2 of them who belongs to the owner. So it's 50% as to whether or not just by random chance you would get it right. It's 50% probability. So the research question is, can humans identify which dog belongs to which owner better than just randomly guessing? So here's the logical trick here. What probability would you expect to get in this study for matching a dog to an owner in this case? Well, again, 2 dogs, 1 owner, so it's 50-50. That's it, it's 50%. Therefore, the proportion correct that we are expecting just by random chance is 50%, because we have 2 dogs, and it's a guess of 1 out of 2. So the random chance result that we would expect is 50%. But our sample here now is 16. So of the 25 dog owners, 16 were paired with the correct dog in this situation. So our sample proportion is above 50%. It's above 12.5. So the issue is, now that we have our research question, we could say in the population of dog owners, depending on how this was sampled naturally, or in the population of people in this scenario, can they match dogs to their owners better than 50%? So here's the thing. How do we make hypotheses out of this? What's the idea? Well, the way I like to think about it is this. We obtained a sample result of 16 out of 25. That proportion is greater than 50%. I will make it my suspicion that there is something that people can do to predict dogs going with owners, that people can predict it better than random chance. That's what I want to find some evidence for here. I'm going to suspect that. Therefore, my alternative hypothesis is that the proportion or the probability of matching dogs to owners is greater than 50%. And therefore, the null hypothesis is that just pure random chance is the only thing going on, and that there's no prediction possible beyond random chance. Therefore, the null hypothesis is that the probability or the proportion is 50%, 0.5. And that's how we set this up in this case for a 1 proportion case. And so let's clarify here. This 0.5 is the population parameter. It is the proportion in the population that people can match dogs to owners. So the uninteresting result, the result of just random chance, is the null hypothesis. We say that the proportion we would expect to get of people being able to match dogs to owners is 0.5. And the thing we suspect might be going on, the interesting result, the thing that our sample data maybe starts to indicate to us, is that the proportion of dogs that can be matched to owners is greater than 0.5. So that's setting the stage for this. So now we need to test this. So again, to conduct this randomization test, we need to look at a world, we need to run a simulation where we assume that the null hypothesis is true. In other words, we need to run a simulation such that the assumption is that the true proportion of interest is actually 0.5. That's our null hypothesis. So we start with this assumption that the actual proportion in the population is 0.5. And we will run a randomization test with that. And we will get some results. After we get our results, we will take our observed result of 16 out of 25, which is about, I think it's 62.5% or 0.625. And then we ask, given that we just simulated a world where 0.5 was the true proportion, how likely or unlikely is it for us to have obtained 16 out of 25, or a proportion of 0.625? If it's unlikely to obtain 16 out of 25 matched in a world where the probability is 0.5, then the probability is probably not 0.5. The proportion is probably not 0.5. And we therefore would reject that null hypothesis. But we need to go actually run this simulation to find out. So, okay, there's some conclusions there that we will get to. Let's actually run it. Okay, so we are doing a randomization hypothesis test for a single proportion. We're doing a proportion because we are looking at the proportion of dogs being matched to owners. Great. So fortunately for this example, it is the default example in the StatKey randomization test for proportion. So here it is, dog matched with owner, it's already in. And just some things to notice here. Here's our original sample data. Oh, excuse me, it's the proportion is 0.64. I did my mental guessing there. Anyway, so here's our sample data, 16 out of 25, or a sample proportion of matching dogs to owners of 0.64, or 64%. Now, if remembering what we do with the randomization situations, you don't need to worry about sort of what's talked about in the book with generating. I mean, there's a little bit of thought that goes into this discussion activity about generating a particular randomization distribution by hand. But we just let StatKey do it for us. But here's the logic, again, reiterating the key points from the book, what the randomization test is doing. In the case of a proportion, the randomization test is basically going to give us our result, original sample back, in a bootstrapped-like fashion. And it will effectively be bootstrapping samples of 25 with, if you wanted to think of in terms of index cards, with 16 saying correct and 9 saying incorrect in terms of matching dogs to owners. And so there will be a sampling with replacement that goes on behind the scenes. And then that will be a bootstrap method. Randomization distributions are simply bootstrapping methods because that represents sampling variability. But when we're done with the bootstrapping part, and this is what you don't see happen in StatKey, you just see the consequence, it shifts the result over so that it's centered on the null value, because that is the world we are existing in. Remember with our bootstrap distributions that they were centered on the sample result, the sample mean or the sample proportion. Those bootstrap distributions were centered around the sample mean or the sample proportion. Well, when we want to simulate a world under a null hypothesis, we have to make the distribution go to that world. Therefore, what we do after we do the bootstrapping method and obtain our bootstrapped means is we basically adjust them so that the middle of our distribution is at the value for the null hypothesis. We just simply move it so that it's at the value for the null hypothesis, because the null hypothesis is the world that we are working with. Okay, so let's do this bootstrapping and adjusting for our null hypothesis. Let's do that 10,000 times and see what we get. And this is the same idea with bootstrapping, where for each randomization sample, we will get a particular result, and we can look at, oh, it is still thinking. Well, okay, while it's thinking, and we can get a particular result just by hovering over and, ooh, still thinking here. That's what happens when you click a button a bunch of times. Come on. It'll eventually come through. Sorry about that. Okay, yep, there we go. Now we are 10,000. All right. We can hover over any one of these. This is 10,000 bootstrapped means that were shifted over so that we would be centered on the null value of 0.5 proportion. And we can move over any one of these and see that a particular result, one of the many 10,000 that's shown right here. So now this is it, and here's the question we ask. Here is what, okay, what are we seeing here? Here is what my world looks like, assuming that dogs cannot be matched to owners better than random chance, better than 50%, better than a proportion of 0.5. This is what my world looks like. This is it. So what result did we get? 0.64. Okay, great. If we got 0.64, how often did 0.64 or something more extreme than that happen? Let's find out how we can do this. Since we're going to just look at 0.64 or larger, I can click the right tail button and I will get my little, come on, still thinking, there we go. I can get my little proportion counter and I can type in my sample result of 0.64. And it will think and think and think. Ah, there we go. Okay, so in this world where the null hypothesis is true, obtaining our sample result of 0.64, matching 16 out of 25, occurred 11.9% of the time. 0.64 or larger in our simulation occurred about 12% of the time. This is our p-value. This is the probability that we obtain our sample result, or more extreme, assuming the null hypothesis is true. So our p-value is 0.119. That's not, I mean, that's not super unlikely. And the issue is this. In statistics, we tend to put a cutoff of 0.05 or 5% as our threshold for what's unlikely or not unlikely. So by that virtue, we say, well, about 12% of the time, that's still pretty likely to happen by random chance if the null hypothesis is true. So I can't reject the null hypothesis.